Hello everyone, this is the first lecture for Math 345. I call this chapter Complex Analysis. I think a lot of people, especially higher level mathematicians, would disagree on the definition of analysis here. So maybe we call this complex numbers or complex functions, and it's just an introduction, so we're just going to get used to playing around with these complex numbers. They are very important for where we're headed, and I want to mention really quick where we're headed. We are headed toward defining e to the tm where t is greater than or equal to 0, it's a real number, and m is a matrix. Okay, why do we need complex numbers to do something like that? I'm just going to mention that really quickly. We need complex numbers because the eigenvalues of a real matrix can be complex. Okay, same with the eigenvectors actually. So both the eigenvectors and the eigenvalues of a purely real matrix can actually be complex, and eigs, I'm just going to say eigs for both eigenvalues and eigenvectors, are very important to the definition of e to the tm. So that's where we're heading, and we really do need to tackle at least a few aspects of complex numbers to get there. So let's do that. So here we're just looking at complex analysis, and here's why I say why the complex numbers. This is 100% directly related to finding the eigenvalues of a matrix, okay? Because the characteristic equation from a matrix, you should remember this from linear algebra, and if you don't, we'll get there eventually. Anyway, the characteristic equation is a polynomial, and the eigenvalues are the roots of that polynomial. Okay, so what does this fundamental theorem of algebra actually say? The fundamental theorem of algebra says if I have an nth degree polynomial, this is a polynomial, it's in n degrees, then I have this set of n complex numbers. Now what does this mean? What is this very special set of n complex numbers? Each bk is a root. Okay, so it says if I have an n degree polynomial, I have n roots. That's what we want to think about. Now what is going on in the middle here? What does this mean? Why am I saying that? Then p of x is equal to this weird notation. All this is saying is that this is, let's define this capital pi. Capital pi is just like capital sigma, but for multiplication instead of addition. Okay, so pi, capital pi, p for product, Greek letter P for product, capital sigma, Greek letter S for summation. All this is saying is instead of our capital sigma notation where we would take the sum from k equals 1 to n, we're taking the product from k equals 1 to n of the expression on the right. Okay, so what is this actually saying here? This is, let's go in blue, this is the factorization. So p of x can be factored into n terms. That's the fundamental theorem of algebra. As long as we use the complex numbers, every n degree polynomial can be factored into n terms. That's all this is saying. Okay, let's move on from there. Now this is really why we're here at the complex numbers, but let's actually talk about the complex numbers really quick. So by their construction, I'm sure a lot of you have heard about the construction of complex numbers before, right? We have this very special number we call I, and we're just defining it such that I squared is -1. It's a number that we have defined so that's purely symbolically, that number symbolically squared is -1. From that point onwards, we get all sorts of amazing properties. What we do to form the complex numbers, which is just the imaginary numbers, right? We call I the imaginary unit. It's the imaginary number with length 1. That's why we call it the unit. So the complex numbers, in fact, are a little bit broader than that. We can have a real part, we call this x a real part, and then we can have an imaginary part we call iy an imaginary part. So really the complex numbers are this like two-dimensional representation of all of the real numbers added to all of the imaginary numbers. And this is one way we represent them. And what's nice about these complex numbers is that we have a very natural set of operations, just like we have for the real numbers, plus, minus, times, and division. And we can define them as the following, right? I'm calling this a proposition just because it's not exactly straightforward to prove, but it's not that hard to prove either. But we just, we have some definitions for how we add, subtract, multiply, and divide. And I shouldn't call these definitions because we can define these operations naturally according to how symbolically they should be represented. And in particular, in the latter two cases, okay, this multiplication version shows up from foiling, right? If we foil things and then group terms in terms of the I terms in terms of the x's and y terms, and we remember that I squared, right? When we multiply iy1 foiled against iy2, we're going to end up with something like a negative because we have an I squared y1, y2, and that's exactly the negative y1, y2 we see right here. But all of a sudden we notice the way I've grouped these is I've grouped them as the real part plus the imaginary part, the real part plus the imaginary part, the real part. So it turns out the two imaginary terms, when multiplied together, turned into the real term, and it's actually the cross terms, y1x2 and y2x1, that cross together to remain imaginary. So that's what happens in the multiplication version. I say that the proof is see the exercise. This will be one of your homework problems. And really the tough one is right here, is this this division term. How do we divide properly so that we can regroup in terms of our standard operations on real numbers on both the imaginary and real part? We can talk more about that part in class. But really, this division part is the tricky part. We have some other definitions here. This thing's called the complex conjugate. The complex conjugate we can think of as just flipping the imaginary part. We take the imaginary part and it starts out as a plus, and we're going to flip it to become a minus. We notate that with an overline or a bar. You can sometimes call it. I'm going to call it overline when you hear me say it, but you can also call it a bar. And here I'm representing an arbitrary complex number as a z. This is common for us to do in math. We notate an arbitrary complex number with a z, and we just define a z as an x plus an iy. Okay, so z is in some ways two-dimensional, but it's also in some strange ways one-dimensional, just because of the way that complex numbers behave. So that's why we have in complex analysis we have this weird duality between one-dimensional complex numbers and two-dimensional real space, which it exists in, if you were to plot it, for example. So that's how we define the conjugate. We're just going to put a bar over something, and that just means make the imaginary part negative. Why is the conjugate useful? Well, it's useful for actually extracting real and imaginary parts. It's a really efficient means of saying, okay, if I just want to extract the real part of z, which, notably would just be x if we wrote it as x plus iy. Obviously, you can just take the iy and get rid of it, and that's the real part x. But if we want to stick in this kind of one-dimensional setting, we can think about the real part as a function of this one-dimensional variable that just takes the variable and its conjugate, adds them together, and divides by 2. And you would see that if you just wrote it out with its conjugate and divided by 2, you would recover x. And then we can do the same thing with the imaginary numbers, or the imaginary part of z. We can take the z and subtract its conjugate and divide by 2i, and that's going to extract y for us. So these are just some nice functions, or you can think about them as parts or whatever you want to think about, where they extract a purely real number. Actually, so the imaginary part of a complex number is considered actually a real number. That's why we've divided by I here. So it sends us into the real numbers, even though we want to think about it as being the imaginary part. We also have this expression called the norm. So the norm, sometimes called the magnitude of a complex number. This is just going to be defined the same way that we would define the Euclidean norm in two-dimensional space R, right? So since these are represented by, basically two real numbers, x and y, the Euclidean distance from the origin of so many units in the x direction, so many units in the y direction is precisely x squared plus y squared, and then you would take the square root to actually recover the distance. So I've defined the norms squared here, but you can always take the square root to get back to the true norm. And this is another reason why it's useful that we have the conjugate, is that it turns out the norm of a complex number is just that number multiplied by its conjugate. And that makes it really useful. I suppose that's the norm squared. Okay, the next step, and this is really half of what we're getting at, aside from, so we had the fundamental theorem up here, right? Fundamental theorem is one of the reasons why I basically have to introduce the complex numbers in this class. The other reason is that analytic functions are very, very important. So analytic functions are basically the complex version of our Taylor series from Calc 2. You'll notice we have this class of functions which are just defined as a series. It's a power series in the variable z, because that's our complex variable, and it has some coefficients a sub n. Now those coefficients I'm going to call a sequence, right? Because they do have an ordering on them. A sub n can be grouped together for all of these n's, and if we group them together, we gain ourselves a sequence. And then we have this special z naught, which is some very special number in C at which the power series is centered. If you remember from Calc 2, all power series have a center to them. Instead of having a center on the real line, we can have a complex center. That's the only difference here. And then there's this very special term, the non-negative number r, which you should remember very vaguely from Calc 2. It's called the radius of convergence. I have that right there. That number is called the radius of convergence. When we're dealing with complex coefficients a sub n, we have to take the magnitude of that a sub n as I defined it above, and then the radius of convergence is actually the limit infimum, but you don't have to worry about this nth part. For this class, it's more than enough to just think about this term as a limit, and we're taking the negative nth root of the magnitude of these coefficients a sub n, and that's going to get us our radius of convergence. Now this is precisely the root test from Calc 2, if you recall. Hopefully that train isn't too loud in the background. This is the root test from Calc 2, and that computes the radius of convergence for us. And so here's how you can see it a little bit later. Down here I say in my remark, for the purposes in this book and in my class, get rid of the infimum and just think about this as the limit of the nth root, 1 divided by the nth root on this sequence, or you can actually compute this via the ratio test. You should remember both the root test and the ratio test from Calc 2 very vaguely. I know it's been a while for some of you, but those let you compute the radius of convergence, and that's going to be very important for us, because when we get to defining this e to the t m, e to the t times a matrix, we're going to care about the radius of convergence. We're going to care that this actually converges in some radius that matters. Okay, so now I'm just going to shift over to some examples of analytic functions. These are kind of any function that's representable with the Taylor series that you remember from Calc 2. These are your analytic functions. That's really the way of thinking about it. If you took a complex analysis course, it gets much more complicated than this. You can do some really amazing things with analytic functions, and they'll sometimes call those functions holomorphic. That's a specifically complex term, holomorphic. But for now, all we want to think about is these analytic functions are those Taylor series functions we recall from Calc 2. So every polynomial is necessarily going to be analytic, which is somewhat obvious because they are Taylor series centered at 0, and they will have a radius of convergence equal to positive infinity. The exponential function, and this is going to be true for any complex rate, the exponential function will actually converge with a radius of convergence of infinity, which is really nice. So that means I can put any complex number in for this power, lambda, or this rate lambda, and I'm still going to get something valid out of my Taylor series. So that's really, really nice. Another great one is the cosines and sines series. For some frequency, it can be true for any complex frequency. Call it omega. This thing that looks like a W is actually the lowercase omega. So any omega I want to put into my sine or my cosine series, it's going to be perfectly valid, and they have radius of convergence of infinity. And then a very common one that we're actually going to use a little bit later on is the geometric series, and this one does not have a radius of convergence of infinity. It should be pretty straightforward to see that if I plug z equals 1 into my geometric series, I'm going to get a meaningless answer, right? 1 divided by 0 is somewhat meaningless. So we can't have this series converge specifically when z equals 1. That seems a little bit obvious that if I take the infinite sum of 1s, I'm going to diverge. But in fact, if we center this at 0, it's not going to converge for any value of z strictly greater than 1 in magnitude. You gain conditional convergence for the rest of the values of z at 1, but that's outside of the point here. So this is one of those cases where we have a non-trivial radius of convergence. And then actually similar with the logarithm. So I put in parentheses here, the natural logarithm, and that I've put a little theta at the bottom. Don't worry about the theta for now, but I'm going to notate natural logarithm in this class just with the letters log. I know it's very common for that to be base 10 logarithm. A lot of mathematicians kind of shy away from that. They will use log log to mean the natural logarithm. This is our favorite Taylor series from Calc 2 as well, specifically the kind that are centered at 1. You can see my center right there is at 1, and that's an analytic function that only has a radius equal to 1. And the reason being that if I plugged a negative number in here, right? We don't know what the log of a negative number is here. So definitely this series probably shouldn't converge. We also have fractional powers. These probably won't be too important later, so I'm going to skip over those really for now. But fractional powers can be represented as a Taylor series, and then I'm going to present a couple examples of functions which actually that are not analytic. Okay, maybe I give myself a little more space here. Functions which are not analytic, okay, because these definitely exist. So you're never going to be able to gain a power series which approximates this absolute value. So this is never going to be analytic. These real or imaginary parts are also never going to be analytic. In many ways, long story short, if it contains the conjugate function is not an analytic function. So if it contains the conjugate function inside of it, you're not going to be able to write a power series that makes that work. Okay, so now we're getting to some of the really cool stuff. A lot of people call this the most beautiful formula in mathematics. This is Euler's formula. So this is really the way of making sense of e to a complex number in terms of real numbers. So Euler's formula, you can think about relating e to a complex number in terms of, now let's look at the real and imaginary parts. We have e to the real part, and then we have cosine and I sine. Sine with frequency of the imaginary part. So that's Euler's formula in a nutshell, is that e to a complex number is really only exponential in the real part. It's exponential in the real part, and it's actually periodic, right? Cosine and sine are classically periodic functions, so we're periodic in the imaginary part with the specific frequency, which is the imaginary part. Another way of thinking about this is the following here: e to the I theta, if we want to restrict ourselves to a purely imaginary power. This is really the true statement of Euler's formula. E to the I theta is cosine theta plus I sine theta. And what this is saying is that if we wanted to represent cosine and I sine theta in terms of a plane, perhaps, I could call this my real plane, my real axis. And this is my imaginary axis. Then e to the I theta actually traces out the unit circle in this real axis, imaginary axis plane that I've constructed, where, you know, if I say I'm sitting there, this angle is theta. So that's pretty nice. That's kind of a very nice way of thinking about e to the I theta. It's just rotations in this real axis, imaginary axis plane, so to speak. We call this thing in purple, we call that the complex plane. And you'll be proving this in your homework, which is very exciting. All right, so there's a nice corollary to this. And that corollary is that you can represent cosine as the real part of e to the I theta, which, if we remember how conjugates work, this is exactly how you would represent the real part of e to the I theta. Similarly for sine, if we remember how conjugates work, we can represent sine as the imaginary part of e to the I theta and then actually represent it in terms of conjugates. There's a few other important complex functions. That's the complex logarithm, which I defined with the Taylor series earlier, but there's a way to define it absent of the Taylor series. And here I'm calling it the complex logarithm of a specific branch. What I mean by that is that just how we remember logarithms don't make sense for negative numbers, they kind of can, and this is how we do it. If we take this Greek letter here is xi, by the way. If we take a xi, that's really fun to say. If we take a xi in the complex numbers, and its imaginary part sits in this interval, right? The imaginary part is a real number. If the real number sits in this interval for some fixed theta, and you let z be a complex number that's representable by e to this complex number, then the complex logarithm just inverts this equation, which is what we would normally expect out of a logarithm, right? It's the inverse of the exponential equation. But technically, we need to include this branch, what we call a branch, and we just need to verify that the power is not sitting anywhere else other than that specific branch. So in my case, we want to be careful. The subscript of the logarithm is not actually the base of the logarithm. Theta is not the base here. It's telling me where I need to restrict my imaginary part of this c that I'm going to be equal to. Now, if this doesn't make too much sense, you don't have to worry. We're not going to be using these logarithms too much. This section is more of a reference manual for if you ever have any questions about complex numbers, you can kind of come back to this section. If we look at complex powers, the nice thing about the logarithm is that it lets us define complex powers. So since the logarithm got defined on a branch, complex powers also are going to get defined on that same branch, and we define them based off the log rules that we love. So, if I use the log rule here, maybe I'll write this out a little bit more explicitly for you. If I use the log rule just on this section, a log theta z, by log rules, I gain the property that a can push itself to the power of z. And so this is equal to log theta z to the alpha. And then if I take the exponential of all of that, my exponential and my log cancel, and I get exactly z to the alpha. So that's how we actually define these. We kind of reverse engineer the log rule to define complex powers. But because of that, we're stuck with branches. And really what you want to think about for branches is just the same way that we can't define the log of a negative number. You can, but you're still restricted to a branch, and a branch is like a negative number in some other direction in the complex plane. It's not that important for you in this course, but just know that that's something that's utilized in complex analysis. Okay, along those lines, I'm actually going to skip some of these next pieces. They're just not important for what we actually care about in this class. We do care about the following. There's this very nice sentence here about the radius of convergence. So the radius of convergence of a complex analytic function actually can be considered as the minimum value for which the derivative does not exist away from the center. That's what that's stating. That makes our lives easier if we ever want to find the radius of convergence. All right, we'll stop there for today and try to complete the exercises in class. See you there.